Good morning, pre-calculus students. This is Mr. Lehman, obviously. I know you've been waiting to hear my voice for a while. I'm going to walk through some notes for our lesson for this week. I might be slightly quieter than usual because it's 5:39 in the morning and I'm in the kitchen and my kids are sleeping. So we'll see how this goes. Anyway, the point of this video is to go through some examples of the next lesson for you. So feel free to watch the video. You can look at the examples on your own as well. I've posted the notes in Classroom, and then I'll be available online for help later today and then each day around the same time from 9 to 10. You can also email me any questions as you go, and we'll figure this out as we go along. So the first lesson is about derivatives of natural base, exponent, and logarithm functions. So I start with this general definition. Limit as h goes to 0, 1 plus h to the 1 over h power equals e. This is a unusual, but I guess common definition of what e is. E is that natural number 2.71828 or whatever that decimal is. And one way to approximate it is to use this limit definition or this limit property. It's kind of like those trig identity limits for sine of an angle over an angle as h goes to 0. And so we're going to take a look at this, but the limit as h goes to 0 of this expression is equivalent to e. So the question is, what happens for very small values of h? Because we're going to have h approach 0. We're saying that as h approaches 0, which makes h very, very small, that this expression is equal to h. So if I take this expression as equal for very small values of h, and I raise both sides to power h, and then do some math with it. So e to the h on the left. On the right-hand side, I use my exponents, simplify to 1 plus h. And then I can rewrite it. And the whole point of this little activity was just to get a substitution that I could use in my process for coming up with the derivative or the formula for finding the slope of the tangent line. So I did all of this just to get this expression, e to the h minus 1 is equal to h. And we're going to substitute that in on the next slide. So we use our limit definition. Remember, a limit definition of a derivative is f of x plus h minus f of x over h. The limit of that as h goes to 0. And that comes from the slope of the secant line becoming a tangent line. So I have e to the x plus h minus e to the x over h. And we're going to simplify this. So that e to the x plus h over h, try to use some tools here. We can rewrite that using properties of exponents. E to the x plus h, we have a base with 2 powers being added, so we can use that property backwards. I highlighted that in blue. That's really e to the x times e to the h, because if you put those together, we know properties of exponents that become x plus h. Now I see that I have 2 e to the x's, so I can factor out e to the x. And then we're going to use our substitution from the previous slide. In the previous slide, we said that e to the h minus 1 was equal to h. Obviously, with an h on top and bottom, I cancel. And so the limit as h approaches 0 of the original function is equal to e to the x. So what we just showed, my highlighter, what we just showed is that the derivative of e to the x is itself. It's the only function that if you take the derivative, you get exactly it. So the derivative of e to the x is e to the x. So it's kind of easy to remember. Here's your rules. They got the original one, the derivative of e to the x is e to the x. And then number 2 is the chain rule. So e to some function u, that's just how they write the chain rule. Derivative of e to some power is the derivative of power times e to the power. All right, so here's some examples. What I'd like you to do is just pause and try out these as you want, or maybe watch me do the first one and then pause and do the other ones. And I'm not going to go through all the examples on all the pages because this video would take forever. It's already 5 minutes. But if I look at this first one, it says f of x equals e to the 2x. So the derivative is going to start as e to the 2x and then times 2. So it started with this because the derivative of an exponential function is itself. And then this 2 out front is like the y prime. It's the chain rule, sorry. So e to the 2x, derivative of e to the 2x is e to the 2x times the derivative of 2x. The derivative of 2x is 2. So for these, you can treat the exponent as a separate function. So on the second one that I just highlighted, derivative of e to the x squared minus 5x is going to be e to the x squared minus 5x, then times the derivative of what's in pink. So again, I'm repeating the original part. The derivative of the function is equal to the function itself, original function, times the derivative of the function. So in the third one, the derivative of e to the square root x squared minus 3 is going to be e to the square root x squared minus 3. So that's right there. But then we have to take the derivative of that power. So my power is going to be a chain rule, square root x squared minus 3. So it's going to be 1/2 as my power, x squared minus 3 to the 1/2. So we take the derivative of that, 1/2 x squared minus 3 to negative 1/2, and then the 2x comes from the derivative of the inside. So there's a lot going on here. The derivative of the original function shows up. Then I have this inside part of the square root. The derivative of the square root gives you 1/2 times something to the negative 1/2. And then the derivative of the inside part is the 2x. So there's some chain rule going on. So go back through and look at those again. Make sure you get those. These examples are all just meant to use the product rule, quotient rule. So you can look at those. I'm not going to go through all of these. I'll just undo the video or undo the solutions so you can take a look at them. This example's in here to show you how to do explicit differentiation. Just notice right here, kind of like the oval tool better. Right here, x times e to the y. For x times e to the y, we have a product of two functions. The first function is x, and the second function is e to the y. So we're going to have to use the product rule. The derivative of x is 1. The derivative of e to the y is just e to the y times y prime, or dy dx. So I take the derivative of both sides, including the right side, derivative of 0. And then let's look at each of these pieces. So right here, that's all going to show up right here. Right? So if I look at x times e to the y, the derivative of the x is just 1. So derivative of the first times the second is 1 times e to the y. Then the derivative of the second times the first. So derivative of the second is e to the y. Derivative of e to the y is e to the y times dy dx. That's a chain rule. Or e to the y times y prime times the first function. There's the x. And the derivative of minus 10x is minus 10. Derivative of 3y is 3 times dy dx. So we get the dy dx by itself. There's 2 of them, so we can factor them out, put everything else on the other side, and you wind up with that expression for your dy dx. Again, go back through that, make sure you understand the connection between implicit differentiation this is the same type of problem using implicit differentiation. You're going to have to do that product rule twice. You're going to have a product rule for this and a product rule for this second part. And then they have you go through the whole process of coming up with the tangent line. So you can work that out. I'm going to pull down the slide just so you can pause it at different spots and see if you can work your way through it. In fact, I'm going to, I'll do that. So there's the first line, take the derivative of both sides. The reason I'm doing this is so you can just pause it and work it out as your own, and then press play and see if you're getting it right. And then the actual tangent line equation is in purple or pink. Okay, so I'm going to pause there because it's 11 minutes, and I'll make a separate video for the second one.